Hello everyone, I'm going to demonstrate how to draw a titration curve for a polyprotic acid, phosphoric acid, before I did acetic acid or describe the one in your textbook. But I'm showing one that you would draw that's not computer generated. That's one of your choices for activities for Dropbox. So first, start with something easy and draw the y and x axis lines. Then you want to label the axes as pH for the y-axis. Please recall when the pKa equals the pH, that's when the acid, which is HA, is equal in amount to A minus, which is the conjugate base that's missing one proton compared to the acid. On the x-axis, you have many types of x-axis, but we're going to focus on moles of OH. You may recall that 1 mole of OH will react with 1 mole of proton from an acid to make water. When you remove half a proton from HA, then you will have HA and A minus and have used 0.5 moles of OH minus, and that will be at one of your pKa's that you'll remove half a proton. And that will be equivalent to half a mole of OH, and that'll be one inflection point. So every time to get to an inflection point where the graph will be level, you'll need to remove half a mole of H plus. So, but first label your axes as shown. And now we're going to titrate phosphoric acid. So I have a picture of it here. So phosphoric acid is H3PO4. It can lose 3 protons. So when it loses 1 proton, then you have H2PO4 minus, and that occurs at pKa. So it has here pK 1, 2, and 3, but or pK. So it should be pKa 1, pKa 2, pK 3. So these are different pHs at which you'll have equal amounts of H3PO4 and H2PO4, H2PO4 minus, and HPO4 2 minus. And then you'll have here at the last pK of 12.3, you'll have HPO4 2 minus and then PO4 3 minus at equal amounts. Okay. Please ignore these equations down here. So right now it's just the same drawing I had on the previous slide, but I've added in the structures of the phosphoric acid. So here I have one pH value here, which corresponds to the first pKa. Okay, I rounded it. So pKa of 2, or pH 2, is when you have equal amounts of form A and B, and that's where it's level here. That's known as an inflection point. But you initially would have started out at pH 0, which you would have had only pH A. The pH wasn't strong enough or not enough base to take any protons off. But when you have this level point at pH 2, then 0.5 moles of OH will take off half a proton, so you have equal amounts of A and B at this inflection point. Next, you'll notice I've added another half a mole of OH on the x-axis. So that means we've taken off a total of 1 whole proton. So that means at this point here, this equivalence point, we only have form B, whereas here where it was level, we had A and B, and where it was near pH 0, we had A. So now we only have B, and that's because we took off a whole proton now as a cumulative effect. But note this pH is lower then 7, our next pK, but higher than 2. This may not be drawn to scale. Next, it's level again. So we have another inflection point. This corresponds to pH 7. When we're around pH 7, we have forms B and C. We have either 2 protons on the phosphoric acid or 1. We have equal amounts of B and C. But to get B and C, you had to just take off half a proton from B so that you could have some B left, 50%, and 50% of C made. So at pH 7, we've used 1.5 moles of OH so we could have forms B and C. So next, you probably guessed we want all of C. Okay, to do that, you're going to add another 0.5 mole of base to get up to 2 moles of OH used, and this will give us all of C. Okay, now I made this very vertical because I'm not using a pH meter. I don't expect you to be perfect either because we're not doing lab. So here at 2 moles of OH, it's rapidly going up the pH because we're in between pKa's. Their next pK is 12, so it's rapidly going up. Okay, and so now we have all of C here. And we've removed 2 whole protons, so that would correspond to form C, because form A had 3 protons. So now, you may notice the axis has changed on the y-axis. I've added pH 12, and we do have a pK of 12, around 12. So that's our last inflection point where it's level, and now we have C and D. But to get to C and D, we added another 0.5 mole of OH and removed 2.5 protons. So we haven't removed all 3 yet, totally. So we have formed C and D here at this last inflection point, which corresponds to 2.5 moles of OH and the pH of 12. So when the pH equals 12, which happens to be the third pK, you have equal amounts of C and D. And the pH is relatively stable until we exceed that pH. And that's shown here, where now what has happened. We still have pHs 2, 7, and 12, which correspond to the 3 pKa's given. Please don't memorize any pKa's of anything. They'd be given to you on a quiz or exam if you needed them. So here we're going to remove the last remaining 0.5 mole of proton left, because we did have C and D to get to all of D. And so it only goes up another 0.5. But the pH rapidly goes up because we have, at that point, no more protons to donate to neutralize any of the base or any OH. So it rapidly goes up. So titration curves always end with the curve pointing up since we've run out of protons to neutralize the base. Okay, now I've also labeled the inflection points, which are all the flat ones. So we have one here, here, and here. So these all match with the pKa's. And again, when the pK equals the pH, you have equal amounts of that acid and its conjugate base. As shown here, a conjugate base, if it still has a proton, can act like an acid later on as you increase the pH to and beyond its pKa. So every time it's level, you have 2 species where it rapidly goes up, and that's 1, 2, 3 times, but I only labeled 1, so I want to be too crowded. You have equivalence points. Inflection point is where it's level and you have 2 species. Equivalence points is where you'd only have 1, and I didn't label those, but there would be 1 here. So if you have A and B, and B and C here, then this one has to be B. So you transition from having 50% B to 100% B, then you go down to 50% B and 50% C, and then this 50% C will go up to 100% C, and then will decrease to 50% C, and then you add a 50% D. And now what's this going to be? Hopefully you came up with 100% D. Now notice here when we have 0.5 moles of OH, okay, and this one's a little bit easier to see. We see we have 0.5 moles of OH, you have equal amounts of A and B. And since it's at the beginning, you can see you're only taking off half of one. And then here at 1, that's equivalent to removing a whole proton. So if you remove a whole proton, you have B. When you remove 1.5, it's harder to see because we don't do halves in these equations. You have B and C. When you remove 2 whole protons, where are we? We're at C. When we remove all 3, then we're at form D. And so notice the number of pKa's is always the same as the moles of OH, which is the same amount of inflection points. And also equivalence points if you don't count the first one. And this here we consider always as 0, which I had on this slide here. Okay, so I hope that explains how to draw a titration curve. You will have an activity later that you get to apply drawing a titration curve to an amino acid, which is in chapter 3. But yeah, if you do it really fast, backwards or forwards, you can see it being drawn. Kind of fun. Okay, thank you. I'm going to try to insert this in the main PowerPoint slide.